Hi guys, so here is, as promised, your first help video for textbook problems. So for chapter 4, unit 4, you have to do 721 and 729 and 31. So let's take a look at 7 first, which says, what average force is required to stop an 1,100 kilogram car in 8 seconds if it's traveling at 90 kilometers per hour? So just like any problem, I would start with a picture. Let's get a sense of what's going on. This is Unit 4, number 7. We have an 1,100 kilogram car that's traveling at 90 kilometers per hour, and we want it to stop here, which is a time 8 seconds later. So this problem I like because it combines what we've already been doing with motion and gets into forces. And what's going to stop this car? Well, a force has to. So we know there's got to be some kind of force provided by the brakes to stop it. And that force is going that way. So I drew a little arrow up there for me. Okay, so we got this car that's going forward. It needs to stop in 8 seconds. How do we get started? Givens, like always. So let's make our givens list. We don't really need to worry about the y direction at all since nothing's happening there, so I'll just have a single column in my givens list for this problem. Some things that I know, well, I got mass is 1,100 kilograms. We got time is 8 seconds. And I got velocity as, or my original velocity in x, because I'll be slowing down, is 90 kilometers per hour. Now, we know this is an issue because we don't like working in kilometers per hour, we like working in meters per second. So I'll leave you to go do the conversion. It's not too hard. Remember, the secret is multiplied by 1. You need help. There's a help video on doing conversions. So we got that stuff in there. And the thing I'm looking for again, it says what average force? So it's asking me force equals question mark, right? Well, that's it. That's all my givens. So what do we do next? Let's try formulas. Now, since I know I'm looking for force, I'm going to start with a formula that has force in it. So the first formula I'm going to put up is F equals ma. Here's my formulas. All right, so F equals ma. Well, can I solve for this? Because if I can, I'm done. Great. Let's see. Force, I don't know that, so I get a question mark. Mass, I know it. It's in my given list. Acceleration, don't know it. But if I can find acceleration, I'm done, right? Okay, so let's go to another formula. Now I'm going to try to find a formula that has acceleration in it. So I'll start with the acceleration formula. A equals v final minus v original over t. Well, let's see. Do I know A? Nope. That's what I'm trying to solve for now. Because if I can find A, I got F and I'm done. Do I know v final? Well, it's not my given list, but if I think for a minute about what's happening in the problem, the car's stopping, right? So that means the v final is 0. And how about VO? Well, I have that. I got to convert it, but I got it. And time, I got that. So I can use this formula to get A, and I can use this formula with A to get F, and I'm done. That's it. Now, I think there might be a second part. Let me look real fast. What average force is required to stop a car? Nope, that's it. Easy peasy, not a bad one. So let's look at the next problem, which is 29. Okay, in this problem you have, at an instant a race began, a 65 kilogram sprinter. I'll come up so you can actually see me. I'm just reading the book. The instant a race began, a 65 kilogram sprinter was found to exert a force of 800 newtons on the starting block at a 22-degree angle with respect to the ground. See chapter opening photos. So there's a picture at the very beginning of the chapter. Let's see if we can find it. There you go. So there's the picture. Let's zoom up. So that's the situation. You have a person is pushing down on the ground, but they're pushing at an angle. You know, they're not just going straight back with the ground. You're pushing down at an angle. So we have to take that angle into account. So it says, okay, you got a 65 kilogram person. They're pushing down at an angle, 800 newtons. What was the horizontal acceleration of the sprinter if the force is exerted for 0.38 seconds? With what speed did the sprinter leave the starting block? Okay, so again, let's start by drawing ourselves a picture. And this is 429. All right, so you have a person who is kind of leading, and they're pushing back on this starting block. So it's kind of goofy, actually, because the person is pushing this way, they're pushing down and back, but because they're pushing into the starting block, which if you've ever ran from a starting block, it's either attached to the ground or you have someone stand on it so it won't move. So really, they're pushing into this starting block, so the starting block pushes them back this way. Now, our picture's really messy now. It's kind of hard to see what's going on. So this is a perfect candidate for a free body diagram. Same thing, free of bodies, there's no body in it. And the result, the thing we really care about, is the effect on the person, not the effect on the starting block. So I'm going to draw this force, which really isn't the person. Really, it's the starting block is pushing me this way, kind of with its normal force. And this is at 22 degrees. So there's our force. We'll call it force of the person, though, FP, which is 800 newtons. So now my question is, well, how does that affect the person? And how does that affect how fast they go? Well, in this problem, different than that one, since this is at an angle, we know we're working in two directions. So let's make our given list again. Givens. And we have an X, we have a Y, and I got a little space up top where I can put things that are in both the X and the Y. So the force of the person, for instance, goes up here because it's in both directions. And that is, I believe, 800 newtons. Well, the mass of the person, that doesn't really have a direction, so that can go up here. Mass equals 65 kilograms. And then I'll also put the angle that we're at, theta, is 22 degrees. Great. I think that's all of our givens. Let me just peek again, check. 65 kilograms, 800 newtons, 22 degrees. What was the horizontal acceleration of the sprinter? Okay, so the question, the thing we're trying to find, is the acceleration horizontally, or acceleration in the x direction. That's our question mark. So we got to get into the x problem. We don't have any givens for that. I can use some of this information to get down here, though. So just like we did with velocities, if I know there's an 800 newton force going up at an angle, I can break that down into a force in the x direction and a force in the y direction. Now all I care about right now is the x direction, so let's just get that. Force in the x direction is force of the person times the, I'm with the angle. Over here I'd be seeing the angle. So Fy would be sine, Fx would be cosine. Cosine of theta. So Fx equals Fp times cosine theta. Now, I don't have my calculator out, so I'm not going to get a number for it, but now I know Fx. So I'm going to write that down here. Fx equals, check mark. I know what it is. It's 800 times the cosine of 22 degrees. Great. Well, I still don't have that much of my given list. Is there any way I could possibly solve this right now? I don't know. Let's see. I'll write my formulas down. And because we're dealing with forces again, I'll start with F equals ma. ma, let's see. I'm trying to find a x. There's my question mark. Mass, yeah, I know that. Doesn't have a direction, so it's not in my x column. But, I have it. It's a scalar. Check. And F. Well, if this is a in the x direction, I want F in the x direction. We just figured that out up here, so I have it, and guess what? I'm done. There's the acceleration in the x direction. Now, you're not really done, though, because it says another part. If the force is exerted for 0.38 seconds, with what speed will the sprinter leave the starting block? So it's given us another given. Time equals 0.38 seconds. And it wants to know what's the v final in the x direction. Question mark. Well, let's see. I got time, velocity, acceleration. I think this is probably another good candidate for my acceleration formula. A equals VFX minus VOX over T. Well, I just solved for A up here, so I got that. My final velocity in the x direction, that's now the thing I'm looking for. That's my new question mark. VOX. Well, I'm starting from nothing, right? The race starts and the person's still, then they start pushing. So this is different than a lot of our motion problems earlier in the year where I would say, start at the instant after something starts moving. I said, let's forget about forces. Let's not worry about what gets things to move. Well, now we are worried about that. So we're worried about that first part of the race when there's only about a half of a second where there's a force going on, but that's what we were concerned about now. So in that case, before the runner starts pushing, this is 0. So that goes away, and in time we know. I have these two, I can get the question mark, problem's done. That's it, not too bad. So let's look at our last one now. This is chapter 4, problem 31. And let me come grab the book again so I can remind myself what it is. A 6,500 kilogram helicopter accelerates upward at 0.6 meters per second squared while lifting a 1,200 kilogram car. What is the lift force exerted by the air on the rotors? What is the tension in the cable, ignore its mass, that connects the car to the helicopter? All right, this is a complicated problem to think about, so we really need to draw a picture. And I'm going to try to slide this computer over because I have a feeling we're going to need some extra space. There we go. And if you need to see the other stuff, you can just go back. So let's take a look at what's going on here. We have a helicopter. That is my sweet helicopter. That is holding up a car with a cable. And it's saying, hey, it's accelerating upward also. So we can start drawing forces on here, and there's a lot of them. There's force of gravity in the car, there's a force of gravity on the helicopter, there's a force from these rotors, the car is being held up by the rope is also pulling down on the helicopter. There's a lot of stuff going on. So rather than try to explain it all in this one picture, what I would recommend is drawing actually 2 free body diagrams. One for the helicopter, one for the car. So here's my dot for the car, and here's my dot for the helicopter. So let's think about the car first, because that one's a little simpler. What's happening in this car? Well, gravity's pulling it down, Fg, on the car. We can figure out how much that would be. We know that the force of gravity is equal to mass times acceleration of gravity. That's not a big deal. Well, how come the car is not falling down? Well, it's being held up by this rope that we're going to label T. So that's the tension, and we haven't really talked about too much yet. So this car is actually being pulled up. So I'm going to write to the side here that it actually has an acceleration. And let me go back to the book to see what it was. 31, 0.6 meters per second squared. 6 meters per second squared. So it's accelerating up. All right, we'll come back to that. Now the helicopter, well, it has gravity pulling on it, Fg. It also has tension pulling down on it now. So that same tension that's pulling the car up is also pulling the helicopter down. Think about it. If you were holding somebody who was fallen off a building by a rope, and then that rope would be pulling you down, that rope would also be pulling them up. So these forces are the same, but they're having an effect in different directions for the helicopter and the car. So the helicopter has gravity pulling it down, it's got tension pulling it down, and then it has these rotors, let's call it FR, pulling it up. All right, so it looks like the helicopter problem is going to be more difficult. So we could solve stuff for this car problem first. Now, I can calculate Fg for the car, and we can actually calculate the tension too, because we found out that there's an actual, I'm going to write an actual acceleration going upwards. When you're actually accelerating, so right now I'm not actually accelerating. Gravity wants me to go down at negative 9.8 meters per second squared, but I'm not. The floor is holding me up. If I were to jump out the window, then I actually would be accelerating. So the difference in those two situations is right now, there's gravity pulling me down and the floor pushed me up. These forces cancel each other out, so there is 0 net force. If I jumped out the window, I'd only have a force pulling me down, nothing going up. So there, I would have a net force equal to gravity, which would make me accelerate at a particular rate. In this case, negative 9.8 meters per second squared. So the fact that this car is accelerating upwards tells me there's a net force. So I can start out by saying F net equals mass times A actual. And I know A actual here. I know the mass of the car, so I can actually find F net. Well, you might be saying, well, how does that help us? Well, F net just means all the forces on something added up. So, in this case for the car, F net is also equal to Fg for the car plus tension. Well, if I can find F net up here, and I can calculate Fg for the car with this expression, then that means I can also find tension. Again, how does that really help us? Well, we're going to apply this exact same process to the helicopter. Now, the helicopter is a little bit different. It's also accelerating up. So we can say, hey, net force for the helicopter is equal to its mass times its acceleration. But F net's a little different for the helicopter. That's for the car. For the helicopter, or I'll call it a chopper. For a helicopter, F net is equal to a few things. It's equal to Fg for the chopper and tension, but there's a third force, and force of the rotor. Now, we can easily get force of gravity for the chopper. We can take tension from here, so we didn't have it, we do now. We can calculate F net for the helicopter up here, and then this is what we really want, force of the rotor, and we can get it. It's a little involved, but we can get it. That's that. Now, let me see, there was a second part to this. What is the lift force exerted by the air on the rotors? Got it. What is the tension in the cable that connects the car to the helicopter? You got that too. So we already did that. We actually did part B first. Easy peasy. So that's it. That's all three problems. I didn't finish them. I didn't do the calculator part. That's where you come in. So if this is a good system, we'll do this for textbook problems from now on. I'll give you some advice to help get started, and then you finish them out, make sure you can do them, and you get credit for them. Good system. Bye now.